Oh,
Yeah, hi Max.
hey.
So,
Today I don't want to do SAT prep because I have my final coming up.
okay, close this off.
Okay, so I have like my textbook here.
Okay.
I don't know if you have the same textbook.
Um, I don't either. What is your textbook's authors?
Stewart, Redlin, and Watson.
No, I have Demana, Waits, Foley, and Kennedy on mine, so I don't have the same textbook. Can you read me certain problems?
Sure. Chapter 1. Wait, I'm trying to find the review. Okay, I think I'm almost done. Okay. Yeah, here it is. So, alright, so the first stuff is the types of numbers and properties of those types of numbers.
Okay.
So, um, like the first question is, it has 4 parts. The first part is in parentheses -3 with a to the 4th at the outside.
Okay.
And then there's another one which is -3 to the 4th, no parentheses.
Like this.
Yep.
Okay. The difference.
Uh,
Go ahead.
3 to the -4th. 5 to the 23rd over 5 to the 21st. Parentheses 2 over 3 to the -2nd. And 16 to the -3/4.
Like that.
Those are 3 different questions, but
Okay.
yeah.
All right. All right, let's talk about the first one. The difference between the parentheses and no parentheses. This 4 applies to everything in the parentheses. So we're going to take -3 and quarter it. Which is equal to positive 81. Okay?
Right.
-3 to the 4th, well, in this case, the 4 only applies to the 3, not the -3.
So it's -81.
So it's -81. In this one, the -4 is an exponent, and the thing about negative exponents is they never mean negative numbers. Okay?
It's a fraction.
Yeah, it's always the reciprocal. So it's 1 over 3 to the positive 4, which is 1 over 81.
And then 5 to the, this would just be 5 to the 2nd, which is
That's correct, which is
25.
Right. So that is 25. Now, 2/3 to the -2, well, you basically take and flip it and make it to the positive 2. In other words, this thing is equal to 3/2 to the positive 2.
Which is 9.
9/4, exactly. And finally, 16 to the -3/4. Well, that's 1 over 16 to the positive 3/4. Now let's look at that. When you have a fractional exponent, the top number is what you're gonna take 16 cubed, and the bottom number is you're gonna take the 4th root of that. Well, it always makes sense to do the bottom number first, just the way they construct these problems. What's the 4th root of 16?
65,000.
No, the 4th root, not the 4th power, the 4th root, meaning we're going to take 16 to the 1/4 power.
2.
2, which means that this is the same as 2 cubed. So it's really 1/8. So again, negative exponent does not mean negative number. 1/8 is a very positive number. But I had a negative exponent.
Okay.
Alright, what else?
There's some scientific notation stuff that they use.
Okay.
So the square root of 200 minus square root of 32.
Okay. When we're simplifying radicals, we want to factor the number 200. And we want one of those factors to be a perfect square. And if we want to be most efficient, we want it to be the largest perfect square we can get. In other words, what factor of 200 represents the largest perfect square factor of 200?
100.
Yeah, so it's 100 times that. Well, what factor of 32 is the largest perfect square number?
25. Factor.
16, right. So it's 16 times 2. Okay. Now this part becomes 10 root 2 minus 4 root 2. How many root 2 is that?
6 root 2.
There's your answer. In other words, once I convert these to the same root, then I can add or subtract them.
Okay, x squared plus 3x plus 2 over x squared minus x minus 2.
Okay. Most of the time when you see a quadratic, it's a factoring problem. Almost,
Okay.
I would say virtually every time. And I have a quadratic in the numerator, and I also have a quadratic in the denominator. What's the numerator factor to?
X plus 2 and x plus 1.
About the denominator.
X minus 1, x minus.
X minus 2, x plus 1. Notice that the two numbers have to multiply to minus 2, always.
Right.
In other words, we're looking for factors of 2.
Okay.
And if you multiply these together, the inside is minus 2x, the outside is plus x. That adds to minus x. So that's the right factor. Now what can we do?
Cancel x plus 1.
Yeah, I can divide top and bottom by x plus 1, and it leaves this. And I cannot simplify that any further.
Okay. There's another one.
Okay.
X squared over x squared minus 4 minus x plus 1 over x plus 2.
Okay. Again, we have a quadratic here. We can't really factor the x squared, but we can factor the x squared minus 4. What does it factor into?
X squared minus 4 is x plus 2, x minus 2.
Yeah, that's difference of perfect squares. Okay, so it's going to be x minus 2 times x plus 2. And the advantage of factoring it is now I can see that one of my common denominators has to have an x plus 2 in it. What
So
is
you can multiply the
what is
whole
my common denominator going to be?
x plus 2, x minus 2.
Correct.
So you can multiply the whole left side by x minus 2.
Well,
right side. Right side.
This is not an equation, am I correct? This is just an expression? This is x squared over that minus this over that?
Yeah.
Okay, so the right side has to be the same common denominator. What's the numerator of the right portion?
X plus 1 times x minus 2.
Yeah, when you're doing these, always make sure that when you're done, you got the same thing you started as. Well, that is exactly what I started with. If you cancel out the x minus 2, you end up with x plus 1 over x plus 2. Okay, now we have a common denominator, and I can operate on the numerators. Well, the numerator is what? What's this part of it? And you do need parentheses. Whatever the numerator is, I'm going to subtract the whole thing. Not subtracting just the first term.
The numerator.
Start there. Multiply x plus 1 times x minus 2.
X minus 2. So it's x squared minus 2?
No. You have to FOIL these two together.
Oh. So x squared minus 1 1x. Yeah, okay.
Okay. And then that's still all over the common denominator. And now I can simplify the numerator. If I remove the parentheses, what do I have?
Wait. X. If you remove the parentheses in the numerator, you have x squared minus x squared
Okay.
plus x plus 2,
Right.
which is x plus 2,
What is that?
which cancels with the x plus 2 in the denominator, leaving you with 1 over x minus 2.
You got it. And that's the equivalent of that expression.
Okay. This one says rationalize the denominator and simplify.
Okay.
So square root of 10 over square root of 5 minus 2.
Like that, or the minus 2's out here like that?
Not like that.
Like this?
Yeah.
Okay. when you have a denominator that's made up of two terms like this, the best way to rationalize it is to multiply it by the conjugate of this term. Okay? So at a minimum, I know I need to multiply the bottom by by root 5 plus 2. Well, if I have to multiply the bottom by that, I have to multiply the top by that also. Because the only thing I can ever do is multiply a fraction by the number 1. Okay? Now, let's do the bottom first. What's root 5 minus 2 times root 5 plus 2?
Root 5 minus 2 times...
Yeah. The reason I'm multiplying it by the conjugate is it's going to eliminate the radical sign. I'm going to have no radical sign when I'm left over. In other words, if I take this, multiply it by that, do it term by term. This times this.
That's 25.
It's actually
it's just
5 because it's the square root of 25. Then this times this plus this times this always cancels. When you're multiplying by the conjugate, that's the reason you do it, is so that the two middle terms cancel.
Okay, so there's 1 plus 1.
No, the last term is minus 2 times plus 2. Correct. So that's minus 4. You're right. The answer is 1. Okay, so that's the denominator, is 1. What's the numerator?
Square root of 10 times square root of 5.
Okay, that's square root of 50 plus what?
1. 2 times the square root of 10.
Okay. Now the square root of 50 can be simplified.
You could pull 25 out of it twice.
Well, once, really. In other words, it's the square root of 25 times the square root of 2, correct?
Mm-hmm.
Okay. So that's 5 root 2 plus 2 root 10. Well, normally I don't simplify root 10 because it simplifies to root 5 times root 2, which is not normally a simplification. But in this case, if I pull a root, let's see, if I want to write this like this, I can.
Which gives you 10 root 5 root 2.
Well, it gives you 5 plus 2 root 5, the quantity, times root 2. In other words, this is equal to that. All I've done is factored a root 2 out.
Okay.
Okay. And I guess this is the way you would want to show your answer, exactly like that. In factored format, in fact, as opposed to this. This is in unfactored format. And like I said, it's rare where you break up root 10 into root 5 times root 2. You don't often do it because root 10 is as simplified as it gets. But if I'm adding that thing to another number of root 2's, then I want to break it up into some number of root 2's. And it's that number of root 2's. So now I have 5 root 2's plus this number.
Also, if you were doing something by root 5's, would it be 2 root 2 5's?
Yep.
Root 5?
Yep.
Okay, cool.
In other words, that's the only time you would ever condense that to a root 5 or a root 2, and that's if it was being added to some other number of root 5's or root 2's. Otherwise, root 10 is simplified. In other words, I'm never going to do this unless I have a good reason. That's simplified. That's one term there. This is two terms. And they're both still radicals. So it's rare that I'm going to do this. Only in this particular problem because I have some number of root 2's already in the problem.
Okay. No mixtures. If I see any more in this chapter that I need help with, I'll do that next lesson.
Okay.
But I want to move on to a different chapter.
That's fine. You can do it. Yeah, and I certainly apologize for not. I guess I fell asleep on the couch. I'm not sure. I must have. Because I had you down for 3:30 and you called it 3:45, so I apologize for that, Max.
It's okay, don't worry about it. Where's the test for this? Where is my test? Oh, yes, there is. Okay. So, what does it mean? So there's a multiple choice here, and it gives a few graphs, but it says, which of the following graphs of the functions, are graphs of functions. Which of the following are graphs of functions?
Okay.
What does the graph of a function look like?
Yeah, the definition of a function is it has to pass the vertical line test. Okay? That does not pass the vertical line test. In other words, if I draw a vertical line, I come across 2 points. So for it to be a function, it has to pass the vertical line test. That passes the vertical line test. In other words, can you pass a vertical line through that and only come across 1 point in the y? Well, I can until I get to that little point right there. So technically, the way I drew it is not really a function because of this end part. But other than that, in other words, I should have drawn.
So there's no
I should have drawn it like that. That's a function.
What's the word on where it never reaches? What is that called?
Hyperbola?
No. Hyperbola have these, but they never. That never reaches zero.
Asymptotes.
Asymptote. So a function can't have asymptotes?
Yeah, for sure. Let's take the following function. X plus 1 over x minus 2. Okay? If I want to graph that, well, the first thing I want to do is draw my vertical and my horizontal asymptotes. Well, you always get the vertical asymptotes by what value would make the denominator 0? Well, that's 2.
So if they didn't give you a denominator, it would be -1?
No. If they didn't give you a denominator, then that's the numerator. And now, the reason you have a vertical asymptote if you're dividing by 0 is because that's the one thing in math you cannot do.
Oh, okay, because it's impossible.
That's the top of everybody's 10 commandments of math. Never divide by 0. So the very first thing you do when you look at an expression is figure out, well, what number would make the denominator 0? Well, it's 2. And wherever you have a 0 denominator, that gives you a vertical asymptote. Well, you also have a horizontal asymptote. And the horizontal asymptote is you take the ratio of the numerator's highest degree over the denominators. And in this case, it's 1 to 1. So I have a horizontal asymptote at 1. Okay? And once I've laid out my grid, now I can graph this thing.
What does it mean if it's 1 to 1?
It means the coefficient of the highest degree in the numerator is 1. There's a 1 right there. And the coefficient of the highest degree denominator is 1, and they're both the same degree. They're both x to the 1. So therefore, the horizontal asymptote is 1. Let's say I had 2x plus 1 over 3x minus 2. Horizontal asymptote is that ratio, 2/3.
So that's not 1 to 1.
No. If I had 2x squared over 3x squared, I would still have a horizontal asymptote at 2/3. In other words, you take the highest degree numerator, and if it's the same as the degree in the denominator, you take the ratio of their coefficients. So in this particular case, it's 1 over 1. Okay? Now,
The only reason I ask that is because it says if the graph is that of a function, is it 1 to 1?
yeah, well, here's what 1 to 1 means. Let's talk about that before I get into graphing this. 1 to 1 means it not only has to pass the horizontal line test, but it has to pass a vertical line test. Or excuse me, the other way around. For something to be a function, it has to pass the vertical line test. For something to be a 1 to 1 function, it has to pass not only vertical line tests, but horizontal line tests. In other words, can I draw a horizontal line and only intersect the function in one spot? Well, not really. Not in that spot right there. I cannot. Everywhere else it is 1 to 1. But because of my sloppiness and the way I drew it, let me draw it a little different. Now that's 1 to 1. I cannot draw a vertical line anywhere in that function and have it cross 2 points, and I cannot draw a horizontal line and have it cross 2 points. And that's the definition of 1 to 1. And the reason it's important is because when you take the inverse of a function, it has to be 1 to 1, or else the inverse doesn't have any meaning. Otherwise, the inverse is not a function. In other words, if this is 1 to 1, so I can take the inverse of it. But if I had a function like this, let's say that's a function because it passes the vertical line test, but it does not pass the horizontal line test.
So it's a function, it's just not 1 to 1.
Exactly. Which means that if a function is not 1 to 1, you cannot refer to its inverse unless you take further action.
Okay.
For example, let's take the sine function. Well, that's a function, passes the vertical line test, but it doesn't pass the horizontal line test. So I can't really talk about the inverse of this sine function. But the only thing is, the inverse sine function is an extremely important function. We want to be able to talk about it. Well, the way we do it, the way we come up with an inverse sine function is we restrict the domain of the original function from minus pi over 2 to plus pi over 2. And now notice that that part of it, I'm not going to be able, almost can. If I restrict the domain of the sine function to minus pi over 2 to pi over 2, it becomes 1 to 1. If I draw it properly, that is 1 to 1. And I can draw its inverse, meaning I can graph the inverse sine function. You cannot have an inverse function unless your function is 1 to 1. So if your function starts out not being 1 to 1, let's take the parabola y equal x squared. Well, that's not one-to-one. It's a function, passes the vertical line test, but it does not pass the horizontal line test, so it's not one-to-one. So if I want to talk about this, the inverse of this function, I have to restrict the original function from there to there, and now it is one-to-one. And I can take its inverse, and its inverse is y equal to the square root of x. And if I graph that in a blue pen, that's what the inverse function looks like. But it's not the inverse function. The entire inverse thing would have looked like this. But what I have drawn in blue there is not a function anymore. It's called a relation. If it's not a function, it's a relation. So I don't want a relation, I want a function. So for me to talk about a function, I have to restrict the domain. Same thing with the sine. Now that I've restricted the domain, I can draw the function, and the function looks something like this. In other words, the inverse function is always a reflection about the line y equal x. Okay, well, the line y equal x is this line right here. So if I reflect the part of the sine function over that line, I get this blue line here, which is inverse sine. But it's only inverse sine between minus pi over 2 and plus pi over 2. Because I had to restrict the domain in order to be able to talk about the inverse even.
Okay.
All right. So that's why they're talking about whether a function is one-to-one or not.
Okay.
If it's one-to-one, you can talk about its inverse. If it isn't, you have to do other things before you can talk about its inverse.
Okay. This is find the local maximum and minimum values of the function and the values of x at which they occur.
Okay.
So f of x equals 3.3 plus 1.6x minus 2.5x cubed.
All right. First thing, let's write this in a better format where we have the x squared term in front. So it's going to be minus 2.5x squared plus 1.6x plus 3.3. Okay?
It's not x squared, it's x cubed.
Like that?
Yes.
Is everything else correct?
Yes.
Okay, so that was cubed. Okay. So, to find the minimum of this, or the maximum, depends on whether you've had calculus. If you haven't had calculus, then you have to put this into your calculator and find the minimum or maximum. Okay? Now, it's easier if it's a quadratic. That's, I guess, why I wrote x squared, because if it was a quadratic, it would look like that. It would be a parabola pointing down, and that's the only extrema right there. Okay? If it's a cubic, well, cubic functions tend to look like this. Okay? They're still functions, but notice that there's a local maximum right there, there's a local minimum right there. So what does this question say again? Find what?
Find the local maximum and minimum.
So you've had calculus?
I have not.
Really?
This is pre-calculus.
Which means, okay, which means they want you to graph that. What kind of calculator do you have? Is it an Inspire or a TI-84?
No, it's not a graphing calculator.
Ooh. Well, that makes it near impossible to find these. If you do not have a graphing calculator. Let me open up Wolfram Alpha, my online graphing calculator, basically. And let's graph this just so you can see how it graphs. Wolfram Alpha is a great little online tool.
Yeah, I know about it.
Okay, you're familiar with it, all right. What was it? It was minus 2.5 x cubed?
X. No, just, yeah, x cubed.
And what's the rest?
Plus 1.6x plus 3.3.
And the beauty of it is it tells you what you put in, which is nice. And so if I look at this graph, now you can answer the question, right? Well, if you had a graphing calculator, you could answer it. Because a graphing calculator allows you to find that point right there. And it also allows you to find this point. And those are local mins and local maxes. So in a graphing calculator, you can pull up the graph and it'll tell you what x coordinate gives you that point. And that's what you're trying to solve for, is where on the x-axis is the y at a local minimum. Well, where I'm pointing right there is one of them. It looks like to be negative 1/2 almost. And then where on the x-axis do we have a local maximum? Well, that definitely looks to be 1/2. The only difference between these two graphs is one is zoomed out and one is zoomed in. So if I want to look closer, I can see where the maximum is, and it appears to be right at x equal 0.5. So that's this point right here, x equal 0.5. Well, most likely this is minus 0.5. So I'm guessing that that's your local mins and maxes, is minus 0.5 and plus 0.5. But what you're looking at is a perfect calculus problem. Calculus is all about finding these local mins and maxes of these higher degree functions.
Is there a way to solve it without a graphing calculator?
There is, by first derivative. It's calculus, though. In other words, how I would do that, tell me if this sounds familiar at all. If I take the first derivative of my function and set it equal to 0, I'm going to find out where my horizontal tangent line. You see the two lines I've drawn here?
Yes.
They're both horizontal, right?
Right.
That's a key thing. Whenever you're trying to locate these maximums and minimums, what you're looking for is the slope of that tangent line to be horizontal. Well, the slope of the tangent line is the first derivative. So the way I get the first derivative here, and I mean, I would find it difficult. If you haven't had calculus, there's no way you're going to be able to do this problem without a calculator. There's the first derivative right there. So that's equal to f prime of x, the first derivative. And if you remember looking at my curve, it was where the first derivative is 0. So if I set this equal to 0, I will solve the problem. I will solve where on my x-axis this is true. Well, that's true when this thing is equal to minus 1.6. In other words, if I move the 1.6 to the other side, this might be all Greek to you. But x squared is now that, and I can solve for x. In other words, x is the square root of that number. Well, square root of that number is not quite easy, but it's, what's the square root of that number? That's x. That's where on the x-axis that your tangent line is horizontal.
Okay.
Okay? Yeah, let's not spend too much time there, especially if you haven't had that. It's a bit puzzling, but what else? There's a huge difference between pre-calc and calc. And the problem you were looking at either has to be solved with calculus or a graphing calculator. Either one. Now, Max, unfortunately, man, I really fell asleep on the job today. I have a 4:30 appointment, I have a 5, and I have one later today. So I'm going to have to go for now. And I will put this down as a 45-minute session.
Okay.
And then we can have an hour session normally that we have on Thursday at 4.
Right.
And again on Saturday at 2 or at 10 a.m. And I apologize terrible for being asleep when you called, but that's exactly what happened. Gosh.
It's all right. Don't worry about it.
Okay. So anyway, I've got to run now, and I will text you the meeting ID number on Thursday at 4 o'clock.
Okay.
All right. Bye-bye.